We will start a new chapter which will consider statics of fluids. So we will see how to study behavior of fluids in static case. To begin with, we should define first what is the pressure at a fluid point. So the pressure is defined as a force per unit area. And when we are considering pressure in fluids, we are talking about a compressive force per unit area. So as you can see in the following figure, if I take a very small element, so it's like a point, okay, and I consider the action of surrounding particles on it, it will be subjected to pressure forces from all directions. And you will demonstrate together that this pressure value is independent of the direction. So whatever the direction we consider, the pressure acting on the point is the same. So the compressive pressure force will act perpendicular to the surface it's acting on. And we note that the surface can be a real surface, as a wall or gate, or could be an imaginary surface, such as one of the boundaries of a controlled void. So what do we mean by this? Sometimes, if you are considering, let's say, a wall, and you are interested in the action of the fluid on the wall, then you can say that I will calculate the pressure acting on this surface, okay? On the other hand, if you take any control volume of fluid in your system, okay? So let's say I have a reservoir and I am interested in what is happening in a certain region of my fluid, then I can define what is called an imaginary surface. So when I draw my control volume, so I specify that I am interested in this region. So this is called an imaginary boundary because it's not a real surface. It's not a wall or a gate or anything that is real, but it's an imaginary surface that is limiting my control volume. Now, let us try to derive together what is the expression of the pressure within a fluid using two methods. First, we will use the macroscopic analysis. When I talk about macroscopic analysis, this means that I am considering a certain control volume of given dimensions. So it's not a very small control volume. When we deal with infinitesimal control volume, it's a microscopic approach. So here we will consider the following control volume of depth h and cross-sectional area A. And we want to derive together what is the expression of pressure at this level here. Okay. To be able to do this, all we have to do is to draw the free body diagram of our control volume, which will show us all forces acting on it. So if we do a small analysis, this control volume is subjected first to the weight, which is a body force. It is subjected, let's say here we have the atmosphere, for example. So it is subjected to the atmospherical pressure force here, which is P atmospheric, or P0 if you want, times A. You have at the bottom level, you have the pressure P that is acting upward, because always the pressure is a compressive force, so it's acting towards the surface. And in the horizontal direction also I have pressure forces, but as you can see, due to symmetry, these forces will cancel out, because from both sides the element is subjected to pressure forces and they will cancel out. So we are only interested in what is happening along the direction. Okay, so if I write the equation of forces along Z, since I have equilibrium, I can say that if I consider this is my Z direction, I can say that sum of forces along Z equals to 0. And now I have first the weight. So I have, and it's acting downward, so minus W. I have this pressure acting on the upper surface, so also it's acting downward, so minus P0 times A. And I have this upward force, pressure force, so it's plus P times A equals to 0. So now let us write the expression of the weight. You know that the weight is given by m times g. And the mass here of this element I am considering, okay, the mass is equal to what? So W equals to m times g. And m is rho times the volume. The volume of the element I am considering is the cross-sectional area times the height. Okay, so this is the volume I am considering. It can be replaced by H times A. Okay, and now if I rearrange the terms of my equation, I will get that delta P times A, which is where delta P represents this term, is P minus P0. Okay, now we will discuss how to deal with this term. So in case, in majority of cases, if it's subjected to atmospherical pressure, you consider that the atmospherical pressure is much smaller compared to the fluid pressure, especially if you are dealing with a fluid of high density compared to the air. So in general, P atmospheric can be neglected compared to P, or in case it's not negligible, we can say that we are just considering, so in case it's not negligible, we cannot eliminate it. So we should not put just P, we should put delta P, okay? So in case the pressure at this level is not negligible compared to this one, then the general equation will be delta P times A equals to rho G times the volume, which is H times A, okay? Also, another approach will be to say that this P is representing, let's say, gauge pressure, okay? So if this is the atmosphere, when I do P minus P atmospherical, this is, if you remember, it's a gauge pressure we talked about. So we said that when we consider the atmospherical pressure as a reference, then the pressure will represent the gauge pressure. So now what will happen is that A will simplify, and we will end up with P equals to rho GH, okay? And this equation will give us the variation of pressure with depth, because higher is H, higher will be the pressure, and at any point, you can calculate the pressure induced by a column of fluid, okay, as rho times G times H. And remember that rho G is the characteristic gamma of the fluid, which is called the specific weight. Okay. So in general, if I do any motion in depth, delta P between the 2 points will be equal to rho G times the depth I am considering. Now, as we said, we can do this analysis using microscopic approach or macroscopic approach. So now if I consider the microscopic approach, then I will take a very small element, infinitesimal element, okay, of negligible, of very small dimensions, and I will do the analysis on it. So the way of thinking is exactly the same, just instead of considering a macroscopic element, I'm considering a microscopic element. So now I will consider, let's say, a cubic element or very small element of height dz. So the height of the element is, since it's an elementary height, so we call it we can call it dz. Okay, so if I'm considering a certain face at level z, then the second phase of my element will be at level z plus dz, and the weight I am considering will be a very small weight. I can put that it's equal to dm, a very small mass, times g. Now dm is rho times elementary volume. So dm is dv times rho g. Okay. Now what is my elementary volume dv? The elementary volume dv is given by the elementary height dz times the elementary area dA. So dA times dz will represent for me the elementary volume dv. Okay. Now concerning the balance of forces, it's exactly the same as in the previous case. We have a pressure from the lower side. We have a pressure at the upper side. Okay. And we have the weight. And in the horizontal direction, we have already, they will cancel out. And due to symmetry, it's a fluid at rest. So the pressure forces will cancel out in the horizontal direction. And now, if I write the balance of forces along Z, what do I have? I have the pressure forces, which are pressure at Z times the elementary area dA, minus, because here it's a downward force, minus pressure at Z plus dZ times dA equals to W. And we can simplify this term here by using the Taylor's theorem. Okay, I will remind you about this theorem. The Taylor's theorem states that if I have a function, I can relate the function at z plus dz function of the value at z. So I can say that p at z plus dz is equal to p at z plus the first derivative of the function times dz plus the second derivative of the function times dz squared over 2, etc. Okay, but I can do a certain approximation. I can neglect all terms of second order. So I will just keep this term. So this is a certain approach that is valid when I'm considering very small steps, dz. Okay, so I can say that I can replace p at z minus p at z plus dz by minus the first derivative of pressure with respect to z times dz, where p prime represents the derivative of pressure with respect to the variable z. So if I replace here in this, if I go back to this equation, I can replace pz minus pz plus dz by dp, okay, by minus dp over dz, which is p prime z, times dz. If I do so, what will happen? Let us replace it together. So I will replace this term by minus dp over dz times dz. So if you look at your equation now, dz will cancel out, dA will cancel out, and you will end up with the following result, that the derivative of pressure with respect to z is equal to minus rho g. This is a differential equation. If you integrate it with respect to z variable, what do you get? You get that the pressure is equal to minus rho gz plus a certain constant. Okay, and how you determine your constant? You determine it from a boundary condition. So let us go back to the previous example here. We will end up with the same result, because if we go back to the same example, okay, if I say here that dp over dz is minus rho g, which is the result I got in my analysis, and I have the condition, if I consider the following frame, z is vertical upward, okay, I know the condition here at z equals 0, we said that p equal to atmospherical pressure, or p0. So if I use this formula, I get that by integration, the pressure is minus rho g z plus a constant. How to get this constant? I use the boundary condition. At z equals 0, p equals to p0. So I end up with p equals to minus rho g z plus p0. Now, if I am interested in z at this location, what is z? Z is minus h, okay, because z is positive upward. So now if I replace z by minus h in this equation, what do I get? I get that the pressure at this level is equal to rho g. So you have z is minus h, and already you have a minus, so minus minus will give you plus. So it's rho gh plus p0. It's exactly the same result we got together. Because if you take P0 to the other side, you get delta P between the 2 points is equal to rho GH. So both way of analysis will exactly give you the same result. So we can deduce that this is the expression of pressure that we get from microscopic and macroscopic analysis. Now, we will derive together that the pressure at a point is independent of direction. To be able to do so, okay, I will consider a certain infinitesimal element with a certain inclined surface. Why I'm considering an inclined surface? Because my purpose is to show that whatever is the angle theta, if I consider a very small element, the pressure on the inclined surface will be equal to the pressure on the horizontal and vertical surfaces. This means that if I consider a point, the pressure will not vary whatever is the direction I am considering. Okay, so to be able to demonstrate this, I will pick any control volume with arbitrary angle theta and do the force balance on it. So let us do this together. First, if I consider the following prism and I want to consider the external forces acting on it, so it's subjected to two types of forces. Okay, you have body forces and you have contact forces. What are contact forces here? So you can have contact forces of several types. You can have shear forces, you can have pressure forces, but here in this chapter we are considering static fluids, okay, that are not, so I'm not considering any shear effects. So here shear is not considered because I'm dealing with static fluids, so no shear effect. I have pressure forces which I should consider. Another type of forces that can act on an element are body forces. When we talk about body forces, there are forces that can be applied at distance. So the most common force is the weight. You have, of course, electrostatic, electromagnetic, but here we don't have these forces. So here we will consider the weight as body force. Okay. So let us do the analysis of and draw the free body diagram. So this is the free body diagram of the prism element, which will represent all forces, contact and body forces acting on the element. So all I have to do then is to take each face and represent the forces acting on it. So for example, if I consider the following face, okay, this face is in plane X, Z, okay? So the dimension here is, this is del X, because I'm considering a very small element, and this is del Z. Okay, and now what I will do is I will consider what is the pressure force acting on this surface. All I have to do is to multiply the pressure acting on it. And since this pressure is perpendicular to XZ plane, so it's along Y. So I have a pressure along Y, so I put PY. times the elementary area here, which is del X by del Z. Okay, and I am done with this first surface. So for the first surface, I have a pressure force acting on it. Now, for the following surface here, this surface is along a plane XY. Okay, so this length here is del Y, and this length is del X. So the elementary area here will be del X by del Y, and the pressure acting on it is parallel to Z, so it's P along Z. Now, I have for the following surface, the inclined surface, I have one side is parallel to X, so this is del X, and the other side is inclined, and I will call this distance del S. Okay. Now, what I will do, I will write the equilibrium relations along a y-axis. Okay, so this is y, and this is z. And let us see what we will obtain for this prism. So if you consider the general Newton law, the Newton law states that sum of forces equals to ma. Okay. Now, in case my fluid is at rest, A will be 0. In case my fluid is moving, A will not be 0. Okay. So let us first write the general relation, and then for static fluids, we will replace the acceleration by 0. So what do we have along y direction? We have first the following force, which is Py times del X times del Z. And we have also the component of the pressure force acting on the inclined surface. Because you can see here that the pressure force acting on the inclined surface has two components. One that is horizontal and one that is vertical. Okay, so since I'm now applying along y-axis, I am interested with this component. And this component is simply the projection of this force. Okay, this force is equal to what? It's equal to the pressure force perpendicular to this surface. I called it PS times the elementary area of the surface. This is the area of interest, which is del S by del X. Okay, and since we are projecting along y, so all I have to do is to do PS del X del S times sine theta, because the projection on y is opposing this angle. So this is the projected component along y of the surface force resulting from the pressure acting on the inclined surface. Now, this should be equal to what? If we are considering the general case, it should be equal to the elementary mass of my prism times its acceleration along y. Okay, and for static fluids, Ay will be 0. Now, what is the elementary mass dm? The elementary mass dm is rho times dv. And since I'm dealing with a prism, you know that for a prism, the elementary volume, the volume is calculated as follows. So it's del z times del y times del x over 2. Okay, because it's the area of this triangle, which is del z by del y over 2 times the depth del x. This is my equation along y. I will use similar analysis. Okay, I will do the same procedure now to project along z. So I will write the second law of Newton along z. And this is what I will get. I will get that sum of forces along z will give me. So first, I have the following pressure force acting upward. So it's plus Pz del x by del y. This is the first term. I have the projection of this force along z. So now all I have to do is PS del X del S cosine of theta. So this is my term. And I have the weight. So for my weight, I have minus gamma times the volume. Okay, you can calculate the weight by gamma times B. So it's minus because it's downward. So minus gamma times the elementary volume del V equals to mass times acceleration along Z. So for the elementary mass, it's the mass of the prism. So it's rho times dV times the acceleration along Z. Now, let us do some analysis for the following relation. So to start with, what is del S sine theta? If I look well at my figure, this is del S. And this is angle theta. Okay, this theta is equal to this one, because you know that from mathematical properties, if I have two lines doing an angle theta between them, if I draw the perpendicular to the first and the perpendicular to the second, the two new lines will do the same angle theta. Okay, so as you can see here in this triangle, we have that del S sine theta is simply del Z. So I can replace here del S sine theta by del Z. And I can replace along Z direction, I can replace del S cosine theta. So it will be equal to what? This is the adjacent side to theta. When I do del S cosine theta, I will get del Y. So I can replace this term by del Y. And now what will happen is that I can simplify del X del Z, del X del Z, and del X del Z. So I will end up with Py minus Ps is equal to rho times del Y over 2 times Ay. And now, even what is nice about this relation is that even if my fluid is accelerating, when I consider a point, del Y will tend to 0. So for static and moving fluids, when I consider one point, Py will be equal to Ps. Okay? So because when we consider a point, del Y will tend to 0. So this is what I wanted to validate, that the pressure at a point is independent of the direction, because whatever is theta, as you can see here, this relation is independent of theta. Whatever is theta, I will get that Py is equal to Ps. This means that if I change my direction, the pressure will remain the same. Okay? And the second relation will give you the following conclusion. Also, for the second relation, you will get, so we replace together del S cosine theta by del Y. What will happen now is that del X del Y and del X del Y will be simplified. So what your result will be here is the following. You will have Pz minus Ps equals to gamma del Z over 2 plus rho times del ZAZ over 2. And here again, since I'm considering a point, del Z is tending to 0. So whenever I consider a point, also Pz will be equal to Ps. So I conclude that whatever is the direction I consider, the pressure on one point will be the same from all directions. Okay? And this information is very important for me to proceed with further analysis. This result is known as the Pascal law, that considers that for a fluid at rest or for a fluid in motion, the pressure at one point is independent of the direction. So this is what we demonstrated together. Now, the next step will be to come up with a general relation, okay, that will be applied to fluid, to static fluids, and can be applied also, if we extrapolate to general cases, we can apply it for accelerating fluids. So what we will do now is that we will consider a cubic element, okay, and we will consider all forces acting on it to be able to draw a general relation for pressure acting on a certain element. So what we will do, we will first, always the first step will be to draw the free body diagram. So if I consider a cubic element and I want to put all forces acting on it, I have here again two types of forces that I am considering. I am not considering shear forces here, okay? Because as we said, our main application in this chapter will be static fluids. So in this case, no shear forces are acting on the element. So we have the pressure forces and we have the weight of the element. Concerning the weight, it's calculated as gamma times the volume, which is del x, del y, del z. Concerning the pressure forces, each face of my cubic element will be subjected to action of pressure forces. And the pressure force is calculated as the pressure at the surface times its area. Okay? Now, what we already demonstrated now is that if I take one point and I move in any direction, the pressure will be, I will start from the same pressure. So if I move along X, it will be P plus something or P minus something. And if I move along Y or Z, it will be the same P plus a certain value. Okay? So now, what we will do is we will use the Taylor theorem that we introduced together in the beginning of this session to determine what will be the pressure on each side. Okay? So if you remember, we said that delta P can be expressed in the following way. So if I know the pressure at this point, it's P, and I moved a certain distance, if I'm moving backward towards this face, okay, then what my motion is minus del y over 2. So I moved a distance of minus del y over 2. So from Taylor expansion, I can express the pressure at this face as follows. It's the pressure at the center point minus del P by del Y. Del P by del Y is the first derivative of P with respect to Y times the displacement I did. Since I'm moving backwards, the displacement I did is minus del Y over 2. So I can consider that the pressure at this surface will be P minus del P by del Y times del Y over 2. And to get the pressure force, all I have to do is to multiply this pressure by the area, the elementary area of the face, which is del X times del Z. I will do the same procedure to get the expression of the pressure force on this face. So for the pressure force on this face, what do I have? I have P, which is the pressure at the center point. Now, since I'm moving in the positive direction a distance, this distance is plus del Y over 2. So now from Taylor expansion, I can write that the pressure at this face is P plus del P by del Y times del Y over 2 times del X del Z. Okay? And now, similarly, when I move along Z direction, okay, since I demonstrated that the pressure at a point is independent of directions, so when I move along Z, I will always start from pressure, the same pressure P. But now, when I move upward, I should have a pressure of P plus del P by del Z times del Z over 2. While for the lower face here, I have the pressure is P minus del P by del Z times del Z over 2 times the elementary area, which is del X del. And now, also I can plot forces along X direction. So I have the pressure on the following face and the pressure force on the following face. And now I will be ready to do the force balance in the different directions.